There we are. Welcome everybody to lecture 6 of Intro to Space Navigation, spring 2025. So we're going to be resuming our discussion of orbital mechanics, kind of a crash course in orbital mechanics. And I think last lecture went on a little long. I think today's going to go a little short, but we'll see how that all plays out. But let me go ahead and share my screen. So as a reminder, this is a review of orbital mechanics. The main point that I wanted to make is that the state of a spacecraft has enough information to propagate itself forward into the future. And I use the metaphor of like a seed, right? Like an acorn has all the information about a tree, but you still need water and sunlight and nutrients and all that. Well, in the same way, if you know the position, velocity, attitude of a vehicle, you can propagate them forward in time if you know the equations of motion, the laws of physics that are governing the system, and all of the right assumptions and all of the right parameters. So there still needs to be a system around the state. It doesn't just like on its own propagate forward, but it kind of has all the information in there. That was the point that I wanted to make. So we started talking about the two-body problem, basic equation of motion for a body orbiting another body. About angular momentum and eccentricity, kind of products or parameters that describe a two-body orbit, which is generally we went through some useful equations about the ellipse, and then we talked about Kepler. And Kepler came up with this really nifty set of equations that allows you to predict the position of an orbiting body as a function of time. We talked about this angle, the angle between you've got the center of the central massive body that you're orbiting. Imagine that you've got some floating direction in space, which is your periapsis. That's kind of your point of closest approach. And then you start to record your position as an angle since periapsis. That angle theta is called true anomaly. That's the idea. So when theta is 180 degrees, you're at the furthest point, or apoapsis. We talked about that. You are able to go between time since periapsis and angle since periapsis using. And then we went through a numerical example. We showed that Kepler's equation is a little bit like a one-way valve, where it's really, really easy just using like a calculator or even some hand math to solve Kepler for time. But then if you want to solve Kepler backwards for true anomaly, your orbital position given time, you need to use some sort of a numerical technique. And that's kind of, in this case, left as an exercise to the review from last time. So what we're going to talk about today, so I should get my drawing tablet out here. We're going to continue our review of orbital mechanics, and we're going to talk about a few other topics. And by the end of the lecture today, so continuing our review of orbital mechanics. By the end of the day today, you'll be able to do homework 1, or at least almost all of it. Today, we're going to talk more about reference frames. We love those. We're going to talk about the parafocal reference frame. We're also going to talk about the orbit elements, which is essentially a set of parameters that you can use to describe an orbit. And in the same way that we've said, okay, if you've got your position and velocity, you've kind of described your orbit, well, then there ought to be some mapping between position and velocity and these orbit elements. You should be able to move back and forth between them, sort of like going to a bank and turning your money that's in your account to money that's paper. Same idea here. And then we're going to go through a numerical example. Where we take position and velocity and go back and forth to orbit elements. And then finally, we will do a primer on numerical integrators. And then we'll wrap up with a discussion of homework 1, but I think I'm going to leave that out of the lecture recording because that's kind of specific to this class. So I'll stop the recording. Everybody's free to go the moment I stop recording, but highly recommend you stick around and we will have an in-depth discussion on what's expected for homework 1. So any questions before we start talking about the parafocal reference frame? All right, good stuff. So let me draw everybody a picture here. So parafocal, sorry, I get a little sloppy with R's, so sorry about that. I'm working on the handwriting. Parafocal reference frame. So what is that? I thought we already went over all the frames that were going to be going on in this class. Well, we've talked about, if you remember from all the way back, about the International Celestial Reference Frame, which is something like the world frame or the global frame in this class. And then we talked about how if you translate the ICRF to the center of the Earth, you get the Earth-centered inertial frame. If you put it at the center of the Moon, you get the Moon-centered inertial frame. And it's just a translation. There's no rotation between these frames. Then there's the Earth-centered, which is some rotation from the Earth-centered inertial frame. There is the Moon-centered moon fixed. We also talked about frames that are fixed in some camera or fixed in some spacecraft. I guess I left out, there's also 2 really useful reference frames which are specific to an orbit or specific to a body on an orbit. So I guess really it's parafocal reference frame and orbit frame, or local vertical, local horizontal frame. So the orbit frame and the parafocal frame, we can describe those with a single picture here. So imagine, first of all, that we've got, well, let's do it this way. I want to decide the best way to describe this here. So I'm going to draw a picture. Don't be too hard on me here. Let's see. So we've got an orbit. This needs to be symmetrical. There we go. And let's say one of the foci of this orbit is here, and then the other one is over here. There we go. And let's say that we've got some body which is orbiting the central massive body, which is right here. And so the vector from the central massive body to the orbiting body here has some distance r and some angle theta. That angle theta is our true anomaly, right? Now, we've said before that this vector here, the vector that goes, kind of points through this point of closest approach, this is the eccentricity vector, E. So we're familiar with that. Now also, and I'm not going to draw it, but coming out of the page is the specific angular momentum vector, H. H always points in the direction that is normal to the orbit plane. So that would be coming out of the page as drawn. Okay, great. Now I'm going to introduce 2 new frames here, and the first one, green for this one. So this is the orbit frame, which has basis vectors E, R, and E theta. And I think we actually talked about these in an example in the last lecture, but I want to formalize it a little bit. ER points radially away from the central massive body through the spacecraft or the orbiting body. So your position is guaranteed to be all in the ER direction. E theta is in the direction of increasing true anomaly. So as theta gets larger, you're going to be heading generally in the E theta direction. Now, not always, right? You're going to have some component of your velocity that's along the E theta direction and some component that's along the ER direction. So then this is the orbit reference frame. You can imagine then there's also a third direction that comes out of the page. You can call that EZ or EK if you want, like IJK. Doesn't really matter. We never really talk about that direction because you think about it, your position is only ever going to be in the radial direction, and you're going to have some radial and some tangential velocity, but position and velocity will never have a Z component in this orbit frame. So we've got an rotating orbit frame where ER points along position vector. E theta is perpendicular to ER, points toward increasing theta. And then I guess you could say, this is supposed to be a theta, by the way. I have a hard time with thetas and zeros. They tend to look similar for me. Maybe someone can sympathize. And then we'll just say Z is perpendicular to orbit plane. Or you could just say it completes the right-handed system. Okay. Now there's another reference frame. I'm going to use orange for this one. And this reference frame is kind of implicit in the picture that we've already drawn. So here, if we just say this E direction, now we're going to call this the P basis vector. And then this direction here is the Q basis vector. And then we also have the W basis vector coming out of the page. So out of page, that's oop. So I guess to be consistent, we should also show EZ is out of page. There we go. So this orange reference frame is specific to this orbit, right? There's nothing about the orange frame that is magical in the way that like the ICRF frame is like inertially fixed. This is fixed in the orbit of the spacecraft. It is generally not rotating. Now, for those of you that are more familiar with orbital mechanics, you know that orbits tend to crank or precess over time. So technically, this reference frame is also rotating. But for the purpose of this class, we're going to treat it as being static. That's good enough for now. This is the parafocal frame, where the P direction points along the eccentricity vector. The W direction is perpendicular to the orbit plane, or you could say it points along the specific angular momentum vector. And then Q completes the right-handed system. Completes right-handed system. All right, so hopefully that makes sense. So what I'd like to do is I'll take a brave volunteer and we're going to work on building the attitude transformation matrix that maps from some other kind of Newtonian or inertial reference frame to this reference frame. So I'll have somebody get your gumption up, and I'm going to say, okay, there's also some other reference frame over here, which is the inertial frame. So we'll say it's got N1, 2, 3. And so then there's also the, for the sake of just being consistent and getting these all in one place, there's the inertial or Newtonian frame. This is also known as the ICRF frame or the J2000 frame. And this has N1 pointing in the vernal equinox direction. We talked about what that means. It's the intersection of the two Earth's orbit plane with the Earth's equatorial plane. Gives you a line which kind of points infinitely in both directions. One of those is the directions that the Earth is with respect to the sun at the spring equinox, and then the other one at the fall equinox. We picked the spring equinox. So that gives us the N1 direction, which is some vector that is just kind of in space that's not some function of something that's moving, except for the fact that the Earth is precessing and so on and so forth. So we freeze the vernal equinox at the J2000 epoch. So this is not new information. This is lecture 2. N3 is the Earth spin axis. and then N2 completes the right-handed system. So just to be consistent. So now what we're after is the attitude transformation matrix from the Newtonian frame to the parafocal frame. But before we get there, this is where I'd like someone brave to pitch in. How do we build the P vector? Maybe I'll do this in orange. Whoever's feeling brave, or I could call on a name.
Just to be clear, are we assuming that the Earth is at the center of the orbit, or no? Or is it just...
We are.
Mhm.
Yeah, so I guess strictly speaking, well, I guess you can have a reference frame that's floating out there. But yes, the Earth is at the center of the reference frame. Yep. So if the P basis vector points along the E direction, then this one's a freebie, right? How do we get there?
It should just be N2, right?
Oh, this N2 is drawn arbitrarily, so I could crank this around any which way. Because
Gotcha.
you imagine you've got an orbit. You can have, let's say this is the Earth. Let's say this is the Newtonian frame. You could have an orbit that's up here. You can have an orbit that's over here. You can have an orbit that's this way. So it's specific to that orbit, if that makes sense. So close but no cigar. I guess as drawn, E is N2. But what I'm looking for is how do we build the parafocal reference frame from some numbers that we might already have?
Isn't E just R hat crossed with H hat? So R like the distance from the center of the Earth and H the angular momentum?
Okay, I should probably specify. Sorry, I realize that I've set this up as too difficult of a problem. So I'm assuming we know your position. So I guess this would be your position vector and your velocity. And then in the last lecture, we saw that we could use this to build E and H. And you could also find A and a bunch of other things, right? So y'all are thinking about this a little too hard. P is just, you take E and then you normalize it. So I'm assuming you've already done the math to find the eccentricity vector, which just pops out of your position and velocity. And then similarly, your W vector points along the H direction. So we just normalize that. Q, on the other hand, doesn't come nicely out of any one particular thing, but we already have two of these. We know it completes the right-handed system. So Z cross X is Y, right? So in this case, it would be W crossed with P. So now we still need someone to help me bring it home. We've got some position vectors, but we want the attitude transformation matrix from the Newtonian frame to the parafocal reference frame. So how do we get there? I'll give you a hint. Let's see. We talked about in lecture 3, when we introduced the attitude transformation matrix, we had an example here. Where did we say this? An attitude transformation matrix is nothing more than a list of basis vectors. So if you can describe the basis vectors of one frame in terms of another frame, you're basically done. And that's where we are, right? We're assuming that we have our position and our velocity expressed in some inertial frame to start, right? Then from that point, it's pretty straightforward. We build P. P is this parafocal frame P direction, and it would be in the inertial frame because that's the frame that we started in. So this is just P1, P2, P3. and then Q1, Q2, Q3, and then W1, W2, W3. We're done. Like once we have the P, Q, and W directions, we just stack them. This is the same thing as saying that this is P transpose, Q transpose, and W transpose, by the way, if you want a more compact notation. But that's it. This gives us the attitude transformation matrix from the Newtonian frame to the parafocal reference frame. And it's relatively straightforward to build this from E and H. And we know E we can find from position and velocity. H we can find from position and velocity. Now, what about the attitude transformation matrix from the parafocal reference frame to the orbit reference frame? I'll have somebody else help me with this. I'll give you a little hint here too.
I don't have the full answer yet, but I'm assuming that since EZ and W are pointing in the same direction,
Yep.
that's just it's like the bottom row is just 0, 0, 1, I think.
Yeah, you basically got it. Now you could take it even a little bit further, right? Do you agree with the diagram that I'm drawing here, where ER and E
Yeah,
theta?
it's basically
Yeah.
the same as it's the same diagram as from the example, where it's just the angle
Exactly.
between it's
So
the
it's the
same
same.
matrix, I should say.
You got it. You got it. So this is the cosine of theta, sine of theta, and 0, negative sine theta, cosine theta, 0, 0, 0, 1. Very well done. So good job recognizing that. So the relationship between the orbit frame and the parafocal frame is that you rotate by the true anomaly to get from parafocal to orbit. Now it's crucial that this is the parafocal to orbit. If we wanted to go orbit to parafocal, we would just take the transpose, right? We know that we can take, if you want a attitude transformation matrix to work backwards, all you need to do is take the transpose. And let's see what else. Oh, here is a good sanity check before we move on. Good sanity check. It ought to be that if you take your position, which is in the Newtonian reference frame, and you multiply it by the Newtonian to parafocal matrix, you'll get a parafocal position. Stands to reason, right? We're just transforming from the Newtonian frame to the parafocal frame. When you do that, you'll get some position in the X, some position in the Y, and then some position that is roughly equal to 0, which should make some sense. So in the parafocal reference frame, it stands to reason that if you're here, your position will have some component in the P direction, some component in the Q direction. If you're here, it'll have some component in P, some component in Q. If you're here, it will be only in the P direction. And I guess if you're here, it'll be only in the Q direction, right? But there's no way to have a position that is in the W direction, because by definition, W is perpendicular to your orbit plane. Now, you might get something that's not exactly 0 because of numerical issues, but if you get something other than almost 0, you've done something wrong. And then also, X stands to reason is your radius of your position, this R, cosine of theta. And then your Y is R sine of theta. So hopefully that all tracks. So this is good to check. Okay, so questions on the orbit frame and the parafocal frame. All right, good stuff. So at this point, we're ready to have a discussion about the orbit elements, which are a set of numbers that we use to describe the orbit of some body. And these numbers are equivalent to having your position and your velocity. So if you've got one, you should be able to construct the other and vice versa. So we want to talk about the orbit elements next. All right. So we're going to assume if you've got your position, we'll say that your position is some R1 in the N1 direction, some R2 in the N2 direction, and some R3 in the N3 direction. And you've also got your velocity, which is V1 in the N1 direction, and V2 in the N2 direction, V3 in the N3 direction. This is 6 pieces of information. You could think of it as X, Y, Z, X dot, Y dot, Z dot. The thing is, nothing about your position or your velocity instantly tells you how big is your orbit, which way is your orbit pointed, things that might kind of make more sense to the human brain. So what we would like is a more intuitive 6-parameter representation. So let me ask this question. How many degrees of freedom, there's that word again, I love degrees of freedom, does a 2D ellipse in 3D space have? And as a warm-up, let me just ask you this question.
2, 3.
We got
Sorry.
something?
Oh,
No, we're good.
sorry.
Oh, was that an accidental unmute? As a warm-up, really quick, if you've got a circle in 2D space, do you see how you've got the radius of the circle is 1 degree of freedom, the X component of the center is 1 degree of freedom, the Y component of center is another degree of freedom. So a circle floating in 2D space has 3 degrees of freedom. It needs 3 numbers to fully describe this circle. And now you might choose to express it some other way. You might say, there's some point over here and there's some other point over here, and it's, you know, but basically 3 numbers gives you everything you need to describe this 2D circle in 3D space. X position, X of center, Y of center, radius. Now, if this were a ellipse, then you need more than just the radius to get the idea across. And if it's in 3D space, then you might actually need some other fun information. So let's brainstorm. What numbers do we need to describe a 2D ellipse in 3D space? And you don't need the whole answer to key in your mind. I'll take partial answers.
Well, for the 3D space, would you need 6 degrees?
Oh, I like that number. Where'd you come up with 6?
Well, because you need more than 3 to describe like where it is, because you need to characterize like position and coordinates and orientation by like 2 each.
So you've said position and you need orientation. So let's talk about that. How about, so let's call it the position of the focus, or the position of the central massive body. So I guess that would basically be the position of the Earth, right? And that's 3 degrees of freedom, X, Y, Z. And then let's keep going. Orientation is how many?
Also 2.
In this case, orientation in 3D space. Remember back to our attitude lecture, it's going to be 3 degrees of freedom. Yep, okay. And we're almost done. Now we've described where the center of the ellipse is and which way it's pointed. We're still not quite done yet, though.
Well, so then would you have to talk about its rotation? Like,
well, I suppose rotation is kind of encapsulated in orientation, right? If you decide, if you take a certain set of Euler angles that describe how the orbit is kind of cranked around with respect to the International Celestial Reference Frame, that's kind of covered in here. But what about something even more simple, just like how big is it?
so like distance?
Yeah, distance. What I like to think of, and you don't have to do it this way, I think in terms of shape and size.
Mm-hmm.
So there's the size of the orbit, and then also the shape of the orbit, because you could have a very large, very eccentric orbit, or you could have something that's smaller and close to a circle. So those are 2 different degrees of freedom. And And I'd say that about does it. If you know the shape, the size, the orientation, and the position of the center, you've described your orbit ellipse. But now I'm going to throw in one more in the same way that the vowels are A, E, I, O, U, and sometimes Y. Here's another one. For a spacecraft that is orbiting the Earth, we don't just care about the orbit itself, we care about where on the orbit the spacecraft is. So I'm going to say angular position of spacecraft is another degree of freedom. So hopefully that makes sense. So there's the shape and size of your orbit. There's which way it's cranked around with respect to your original frame. There's the position, the XYZ of the center of the orbit. And then you'll need at least 1 degree of freedom to say, well, where on the orbit is the spacecraft right now? So those are everything that I care about, at least for now. So we can start to name some of these, because actually we're almost done enumerating the orbit elements right now. There's only going to be a few new ones here. So we know the focus is at the center of the massive body. So the Earth, basically. So that's kind of like a duh. Like if we're orbiting the Earth and the center of the ellipse is the Earth. So, okay, we're not really going to think about those. We definitely need to learn about orientation. So there's going to be 3 values, and we don't know about these yet. This is omega, I, and omega. But what these are a set of Euler angles that describe the Newtonian to parafocal conversion. So you could think of it as, we already have this matrix, Tn to Pf. It's an attitude transformation matrix. It's 3x3 that maps from the Newtonian frame to the parafocal frame, or from the ICRF frame to the parafocal frame, right? If we boil that down to 3 Euler angles, that's them, omega, I, and omega. So we'll talk about how to do that in a minute, but hopefully that makes some sense. Shape and size, well, shape is eccentricity and size is semi-major axis, okay? And angular position of the spacecraft, well, that is your true anomaly. So this set right here is the 6 classical orbit elements. Now, there's some textbooks and some authorities that will say that the specific angular momentum h belongs on this list and that a doesn't belong on this list. It's kind of up to you which one you want to use. I like a because I just like to know how big is the orbit, which kind of makes more sense to me. But the specific angular momentum, lowercase h, also includes information about the orbit. And actually, if you'll allow me to click away for a minute, h and a are related by this equation right here. So if you know one, you know the other. Right. So some people will say H, I say A. It's a matter of preference. These are the orbit elements. So we know 3 of them already. We're well acquainted with eccentricity, semi-major axis, and the angular position of the spacecraft, the true anomaly. Let's talk a bit more about these 3 here, which hopefully it kind of makes sense in your head where we're going with this. We're going to talk about collapsing a matrix into 3 Euler angles. And hopefully that makes a lot more sense in the context of the attitude lectures that we've already had. But let me draw you a picture. In the picture, feel free to key in your mic and ask any questions that come to you. Let's say there is a spacecraft that orbits like that. So this is the orbit of the spacecraft. This is the Newtonian reference frame, and 1, 2, 3. And let's say that the point of closest approach is right here, which means that this, actually, I'll draw it this way. This is the P direction. I should probably start it in the middle. That's the point of closest approach. Then we know that the Q direction points out this way. And then the W direction is this way. And this is meant to be a 3D plot. Hopefully this kind of makes sense. W is perpendicular to Q and P. P and Q have no specific relationship to N1, N2, and N3. So I'm trying to show like two different like X, Y, Z, and then X, Y, Z. Hopefully that makes some sense. Now, how do we get from the Newtonian frame to the parafocal reference frame? Well, we're going to do it by a sequence of 3 rotations. So first of all, in addition to all these other things that we're drawing here, let's say that we've got a, you know what? You can keep it in your notes. I'm going to erase Q because I think there's enough going on and this is about to get really busy. But there's nothing wrong with having Q in your diagram. I want to get this across though. There is a line here. Hopefully this kind of makes sense in 3D space here. The spacecraft is below the N1, N2 plane here, below the plane, at the N1, N2 plane, above the N1, N2 plane. And then it's above the N1, N2 plane for a little while, above, at, below. Hopefully that makes sense. So this is the intersection of the PQ plane with the N1, N2 plane. Whenever two planes intersect, in general, you get a line. Now, because this point right here is where the spacecraft goes from below to above the N1, N2 direction, we have a name for this, and this is called the ascending node. Okay. Now, the ascending node is going to be a line in the N1, N2 plane. So what I'm going to do is describe an angle from N1. Actually, you know what? I might color code this. I love using color code. Let's do purple. This feels purple to me today. Here we go. So the angle between N1 and the ascending node is going to be called capital omega. And those of you that are familiar with astronomy, you might know that instead of like azimuth angle, like the horizontal angle, and then elevation, like most mechanical engineers, when you think of angles, you think of azimuth elevation. In astronomy, we say right ascension and declination. So the right ascension is the horizontal angle of some star in the sky, and then declination is the vertical angle of some star in the sky. So this angle here, I can draw a better omega. Let's try again. Is the right ascension, or the azimuth, of the ascending node. Some people will abbreviate that as RAAN. I just do capital omega. Okay, that is actually an Euler angle. Maybe you kind of see where we're going with this, maybe not. We'll get there though. Now, maybe you might also see that the plane is inclined with respect to the N1, N2 plane. So the orbit plane is not the same as the N1, N2 plane. And the angle between them is the angle at which the orbit is inclined. And so I'm going to use, maybe I'll use red for this one. So the angle at which the orbit is inclined is called the inclination angle. So I is inclination. And that's the one that makes the most immediate sense to us. So you can just imagine in your head, if here's the Earth, and you've got one thing that's orbiting here, it's on a nice equatorial orbit, and then you've got another thing that's orbiting all the way up here, well, that thing's at an inclined orbit. That's its inclination angle. So that part should make some intuitive sense. And then the last one, okay, is the angle. Maybe I'll use green for this one. Or blue. Let's do blue. That way we've got like purple, green, and purple and red and blue for our orbit angles here. So once you've cranked over by some amount capital omega to describe the ascending node, and then cranked up by some amount I to describe the inclination of the orbit, then you're going to need to crank around again from the ascending node to the periapsis point, which is omega. And so little omega, and yeah, it's confusing. We've got a big and little omega, is what's called the argument of periapsis. And then from here, if you've got a spacecraft which is orbiting at this point, then it'll have some position, r, and the angle between r and periapsis is theta. Right? That's our familiar true anomaly. So those are all the angles that are involved in describing the position of a spacecraft. But now hopefully we can see that these angles, which have some physical meaning, this is the, and actually, while I'm at it, this angle here between N3 and omega is also inclination. It's the same angle. Okay. So the omega I and omega is actually an Euler angle sequence. It is not roll, pitch, and yaw exactly. It's a little bit different. So you could think of it this way. This is an Euler rotation sequence. So is this an XYZ rotation or a ZYX rotation or an XZX rotation or a ZXZ? Or remember that there's a whole bunch of different ways that you can rotate. How would we describe this as a rotation sequence? Any thoughts?
Isn't it a 3-1-3 rotation?
Very good. It's a 3-1-3. So the first rotation, you're rotating. Imagine you start with the Newtonian frame. You rotate about N3. So this is, you rotate omega about N3. And then that would give you some temporary frame A. And then the second rotation is inclination. But what are you rotating about? We're rotating about the ascending node. But the ascending node is what the N1 frame maps onto. So after you've rotated capital omega about N3, the ascending node is the new x direction temporarily, right? So you're rotating I about the x direction, which is the ascending node in this case. Okay. And you could think of this as a z rotation. You could think of this as an x rotation. And then rotation number 3 is you rotate omega about, in this case, it would be the orbit normal plane direction, which would be W, if that makes sense. And that's a Z rotation again. So this is a 3-1-3 or a ZXZ sequence. All right. Well, from there, that means that we should be able to come up with a series of 3 matrices, right? So what I would contend is that if you took the matrix that describes this first rotation, rotation number 1, so this is rotation number 1, and I'm going to erase this later, so don't write row 1 in here. I'm going to erase that later. If you have a matrix that describes rotation number 1, and then you have another matrix that describes rotation number 2, and I'm going to erase this, so don't fill that in. And then you have another matrix which describes rotation number 3, that if you multiplied those all together, what you would be left with is the attitude transformation matrix from the Newtonian frame to the parafocal frame. Okay, so what is rotation number 1? Well, it is some amount omega. So we're going to start off with cosine of omega, sine of omega 0, negative sine of omega, cosine of omega, 0, 0, 0, 1. All right. Now, somebody help me out. Rotation number 2, now we're doing an x-axis rotation. What goes in here?
Fairly sure it starts with 0, 0, and then 1. And then
Actually, well, very close. 1, 0, 0. Yeah, because in this case, the x-axis is the thing that is unchanged by the rotation. So your 1's always going to be on the main diagonal. But yep, and then what?
then cosine, sine, negative sine, cosine.
Yep, of the inclination. Very good.
Yep.
Cosine, sine, negative sine, cosine. And for the last rotation, good job. For the last rotation, we are rotating about the z-axis again. And we're rotating some amount omega. And so what's that going to look like?
The same as the first rotation, but with omega as the angle.
Exactly. Yep. Very good. So this is cosine of little omega, sine of little omega, negative sine of little omega, cosine of little omega. Right. And then just for flat it out for you, so you don't have to. So buckle up. We're going to fill this in. Here we go. This is negative sine capital omega, cosine of I, sine of little omega, plus cosine of capital omega, cosine of little omega. Then the next element is cosine of capital omega, cosine of I, sine of little omega, plus sine of capital omega, cosine of little omega. And then mercifully, we have a simple one. Sine of I, sine of omega. And then we've got negative sine capital omega, cosine I, cosine little omega, minus cosine capital omega, sine of little omega. And then cosine capital omega, cosine I, cosine of little omega, minus sine capital omega, sine of little omega. And then mercifully, we have a simple one, sine of I, cosine of omega. And then the bottom's not so bad. Sine of capital omega, sine of I, negative cosine of omega, sine of I, and then the bottom right is the easiest one of all. It's just the cosine of the inclination. Whew. Now, I would not recommend coding this up. I don't do this. This is for your information. This is how it all works out. If you find the need to convert from Euler angles from omega I and omega to the attitude transformation matrix, I code this up because it's easier to kind of check yourself. I don't recommend coding this up, but you could if you want to, if you're just into suffering. Now, what's crucial here is that this is also P1, P2, P3, Q1, Q2, Q3, W1, W2, W3. Remember that? The Newtonian to parafocal reference frame, if you can build the P basis vector and the W basis vector and then construct the Q basis vector, you get this matrix. So now you can arrive at this matrix either from E and H, which themselves come from position, this matrix from the angles, omega I and omega. So this matrix is kind of the middle of the road when the time comes to convert between the position and velocity to orbit elements or orbit elements to position and velocity. You're going to need to build this matrix either way. So hopefully it makes sense that we can build this matrix from omega I and omega by doing this series of rotations. You can just code this up in MATLAB or Python. You can also build this matrix from position and velocity with the equations we've already seen. Now, if you wanted to get the orbit elements back out, that is a little bit tricky. So I'll open this as an exercise to the reader. What is omega given this matrix? Or actually, let's start with the easy one. What is I? If you have this matrix numerically, you just have 9 numbers, how would you back out the inclination?
Take the inverse cosine of W3.
Exactly right. It is the arc cosine or the inverse cosine of W3. Or you could think of it as the arc cosine of T3, right? The third element of this matrix. It's the same thing. All right. What about little omega? Going to be a little bit trickier now. Well, it's definitely got something to do with this term and this term. Hopefully that makes sense.
Take either Q3 or P3, divide it by the sine of I, and then if it's P3, you take the inverse sine of that quantity. If it's Q3, you take the inverse cosine.
Yep, that would do it. That would do it. There's actually something that's even simpler than that. But what you said was absolutely correct. If you just take these two numbers and you divide them, the sine of I cancels out. The division of these two numbers, we're going to call this maybe T13 divided by T23, is the sine of omega divided by the cosine of omega. That's just the tangent of omega. So we're going to do an arctangent. We're actually going to do a modified arctangent. Those of you that are familiar with MATLAB or Python, there's arctan2, which is basically, it takes the sign, S-I-G-N, positive or negative, of the numerator and the denominator, and it does an automatic quadrant check for you. So I love arctangent 2 because it does a quadrant check all for you. This is arctangent 2 of T3 comma Q3, which is the same thing as arctangent 2 of T13 divided by T23. And then by that same logic, somebody else help me finish it up. How do we get capital omega?
It would be the negative arctangent, or no, it would be the arc. Is it negative arctangent? Or would it
Let's see.
be a tan 2, and then it would be like the W2 would be negative.
Exactly. Yep. Very well done. Which is also the same thing as a tan 2 of T31 and then negative T32. Very good. So these equations allow you to get I and then both omegas from the matrix. And then these equations allow you to build the matrix from I and then the two other angles, right? And so hopefully we start to see that we have enough information to go from position and velocity to all the orbit elements, or all the orbit elements to position and velocity. And that is exactly what we're going to do, first of all, in the homework. Like, that's definitely coming up. We're going to do it as a numerical example next, after we take a 10-minute break. So why don't we say it's break time. It is 5:56 for me, so it's 6:56 for you. Let's come back at 7:07.
I got a quick question about the parafocal frame, if that's okay.
Yeah, I got a quick answer.
You said that the position and velocity could only be in the p hat and the q hat vector, but can't you like do a burn in the w hat vector to like change that inclination, and then you would have some kind of aspect in there?
good, very good. That's a great question. So if you were to do an orbital maneuver, which we don't really talk about maneuvers that much in this class because that's kind of a control problem, but absolutely, if you did an orbit maneuver, suddenly you've changed your velocity, and now there is some velocity in the W direction. But here's the thing, you've also changed your orbit, right? And if you change your orbit, you've also changed your parafocal reference frame. And the new parafocal reference frame, after you do the orbit maneuver, will have a W that is still perpendicular to your position and velocity.
So is it a condition of the parafocal frame that W is essentially 0 all the time?
Always, yep.
Uh-huh. Okay, thank you.
But that's a great question. So yeah, so hopefully that makes sense. If you do an orbit maneuver, you change your parafocal frame.
Yep, that makes sense. Thank you.
Good stuff. That's a great question. Right, time to start. Hopefully everybody had a good break. So we're about to do a numerical example, and this will absolutely be on homework 1. So this is a good thing to pay attention for here. So example. Position and velocity back and forth with orbit elements. And I did borrow from Howard Curtis' textbook. So this is the Curtis book. Example 4.3 from the undergraduate orbital mechanics class that I took. So we're going to start with position. This is with respect to the Earth. Is negative 6,045, negative 3,490, and 2,500. And this is in the Newtonian, or the ICRF frame, and the units is kilometers. Now, velocity is negative 3.457, 6.618, and 2.533 in the Newtonian frame, and this is kilometers per second. And we also know that this is the Earth, and for the Earth, mu, and you could just look this up if you wanted to, mu is the mass of the Earth times Newton's gravitational parameter, works out to be 398,600 kilometers cubed per second squared. Absolutely a crib sheet number if there were exams in this class. So the question then is, solve for theta E A capital omega I little omega. All right, so here's how I would recommend starting. H, specific angular momentum vector, is R cross V. Not going to get much simpler than that. You take a cross product. After that, I would say, well, H, the scalar, is just H, the vector, normalized. We're going to need that H, the scalar. E, the vector, is velocity crossed with specific angular momentum divided by mu minus R, the direction. So R, the vector, divided by R, the scalar. And E, the scalar, is E, the vector, normalized. So those equations we knew from the last lecture. And if we do this, we'll find that E, and I'm going to give you the number so you can hopefully, in between now and solving homework 1, you try coding this up, and then you can use these numbers to check your math. So we're already done. We got one of them. So E is check. Okay. Next, A is H squared divided by mu 1 minus E squared, which works out to be 8,788 kilometers. So A is now done. Again, nothing new. We did that last time. And also, it's a good kind of vibe check. A semi-major axis should be on the same order of magnitude as your position, right? Generally. Now, it kind of depends on your eccentricity, but you probably shouldn't have a semi-major axis and then a position that is 1,000 times greater than that. That would be unlikely, right? Okay, that seems about right. Let's keep moving. Next, we can say, okay, P basis vector is the E vector normalized. So we just want the direction, not the magnitude. W is the specific angular momentum vector normalized. So we just want the direction, not the magnitude. Q completes a right-handed system with W and P. And T Newtonian to parafocal is just P transpose, Q transpose, W transpose. All right. Hard to do by hand, very simple to code up. So from here, inclination is the arc cosine of the third element in the W direction. And if you convert to degrees, it is 153.25 degrees. There's one of your answers. Inclination, done. And then little omega is A tan 2, T3, Q3. And if you convert, that works out to be 20.07 degrees. Check. And then big omega is A tan 2, W1 negative W2. And if you convert to degrees, that is 255.3 degrees. Actually, you'll get a negative number, but then the negative number plus 360 gets you 255, right? Same idea. Okay, great. So now we're almost done. We just need our theta. Now, we did have an equation for theta back in lecture 5. I'm actually going to skip it because it gives me anxiety to use the arc cosine equation to get theta from R, because arc cosine is wrong half the time. You need to do a quadrant check. I'd rather solve for theta given position in a way that has a quadrant check either built into it or in a way that you can't possibly screw up. I want to make it engineer proof. So what I recommend doing, and I kind of mentioned this already, is if you convert from the Newtonian to parafocal frame the position that you're given at the beginning of the problem, you'll get the position in the parafocal frame, which is x, y, and 0. And if you follow from this, theta is A tan 2, y comma x. And you should get 28.44 degrees. Boom. And that's it. That is position velocity to orbit elements. Very straightforward to go through and code up. I recommend doing this as a warm-up for homework 1 because this is absolutely a part of homework 1. Now, questions on this? Otherwise, we're about to go backwards.
I guess I have just a really quick question. If we know how to do a quadrant check, would you prefer us to do it your way or do the quadrant check?
You can do whatever you want. I will never check to make sure you use my preferred method. Yeah, go for it. A good question. I appreciate you doing that. Okay, so now we're going to go backwards, which is theta E A capital omega I little omega, and we want position in the Newtonian frame, velocity in the Newtonian frame. All right. And the way I recommend doing this, well, actually, you know what? Let's do this all together as an exercise rather than just me kind of vomiting out the equations. How would you start if you knew these 6 numbers? And I guess there's a couple of different possible first things you could do, but where would you start trying to reconstruct your position and velocity?
If we have the omega I and omega, I'd start with building the transformation matrix from one to the other with all the sines and cosines.
Absolutely, let's do it. And we are not going to do this one, but we'll do this one. As a matter of fact, I'm going to be a little bit lazy and just do this. Sorry, it's because I'm on OneNote. I can. There you go. I know y'all are doing this by hand. There we go. But that is. There we go. And that gives you a 3x3 matrix, which is just P1, P2, P3, Q1, Q2, Q3, W1, W2, W3. Okay. And I would also recommend, this will be handy as well, that you build the parafocal to orbit frame from before. which is, if you remember, cosine of theta, sine of theta 0, negative sine of theta, cosine of theta 0, 0, 0, 1. Okay. So those matrices are going to be super helpful. What else can we do to kind of crack the code here?
Once you have that matrix, you have the P vector, the Q vector, and the W vector. And so you can kind of go backwards. So you know the P vector is related to the eccentricity vector. So on.
I like that. So the position gives you the direction of eccentricity, although the magnitude of eccentricity was lost somewhere along the way. I actually didn't think about it that way before, but I bet you could do something really clever in that direction. Let me show you a rather dumb way to do it, which is the way that first occurs to me, at least. But this is the way I see it. Hopefully this makes sense. Let's work in the orbit frame for a second. So remember, to here, orbit frame is ER and E theta. So would you agree that in the orbit frame, your position is lowercase r, ER? Right? There's none of your position is in the E theta direction, kind of by definition, because R is rotating with your spacecraft, and none of your position is in the... So I'm going to say that our orbit is literally just R0, 0 in the orbit frame. Now, we don't know what R is yet. That's fine. We'll figure it out. I would also say that V orbit is, well, you've got some radial velocity term and you've got some tangential velocity term, but you can rest assured that none of your velocity is in the third direction in the orbit frame. Okay. This is where we bust out the familiar equations here. R is equal to h squared over mu, and then in parentheses, 1 plus e cosine theta. Okay, well, how does that help us? Well, also remember that h squared is a mu 1 minus e squared. Okay, and we know a, we know mu, we know e. Okay, so far so good. So this allows us to reconstruct r, the scalar, and that allows us to reconstruct r, the vector, in the orbit frame. And then you might also remember that the radial velocity from last lecture is mu over h e sine theta, and the tangential velocity is mu over h, and then in parentheses, 1 plus e cosine theta. So this is why I like the orbit frame, because position and velocity are so easy to put together. Bam, 3 equations, I guess technically 4 equations, and you've recovered your position and velocity. But that's not what I asked for. I asked for the Newtonian frame. So will somebody help me bring it in for a landing? How do we get the position and velocity in the Newtonian frame?
Multiply it by the transpose of the big matrix you made with the multiplication of the matrices.
Yep, absolutely. So in this case, it would be, I like to think right to left. So it's the orbit frame position. So we need t that goes from orbit to parafocal. Parafocal is kind of like our halfway point. And then we also need t that goes from parafocal to Newtonian. Okay, well, we don't have either of those. We have the transposes of them, but that's fair enough. You would take t p to f, pf to orbit, transpose it, and then t n to pf, transpose it, right? And then similarly, velocity in the Newtonian frame is t parafocal to Newtonian, t orbit to parafocal, velocity in the orbit frame. And if you code this all up, which I encourage you to do, you had numbers that you started with, and there's a good sanity check for you. Your position and your velocity should be the same as you started. And that's it. So that is a subset of the things that you'll be asked to do on homework 1. I hope that makes sense. Questions on orbit elements, position, and velocity? Are we feeling good? All right, good stuff. Sorry, just stretching for a moment here. My hand's cramping on me. So the next thing I want to do, and this will be the last thing that goes into the recording, is a quick discussion on numerical integrators. So part of the homework assignment asks you to start with a position and a velocity and to integrate them over time by basically just solving the equations of motion over and over and over again. And you would use that using something like, if you're familiar with MATLAB, ODE 4.5 or RKF 4.5, or if you're familiar with Python, scipy.ode scipy integrate ODE int. So we're going to talk about how to use those in case you haven't used them before. And that'll be the last thing we discuss today. So a quick primer. On numerical integrators. And the way that I like to illustrate this is with an example. Those of you that have taken spaceflight mechanics with Dr. Kurt Anderson at RPI might be familiar with the pendulum problem. He kind of gives you this problem partway through the semester to make sure that you know how equations of motion work. And we're going to very quickly talk about how you would solve the pendulum problem using, I'm going to mostly be using Python in this course. So we're going to talk about scipy ODE int. But the same thing works in ODE 4.5 if you insist on using MATLAB. So really quickly, if you've got a pendulum and it's got some rest, and that pendulum is going to have some length L, it's going to have some angle theta, which describes its position. It's going to have gravity acting on it. It's going to have some mass. And let's say that there's some coordinate system that it's all working in. We've got some coordinate system here. Okay. You might be familiar that the equations of motion of a pendulum is that theta double dot, so the second derivative of angular position, is negative g over L sine of theta. So mass actually doesn't factor into this at all. Okay. So negative g over L sine theta, that's just a Googleable, like that's the equation of motion for a pendulum. You can also go through and derive it, which is part of the exercise in the pendulum problem. We're not going to be doing that. Now, the way that you need to think about using a numerical integrator is it takes in a whole bunch of states. So state like position and velocity. Maybe the state of this pendulum would be theta, and then also its derivative, theta dot, right? You need to know the derivative of the pendulum to be able to propagate forward in time. So the way that I like to think about this is you'll need some function, which I'll just call func for now. Can't stop the func. And it needs to take in theta and theta dot. And it needs to output the derivative of the state, theta dot and theta double dot. You can see how this would generalize up to x, y, z, x dot, y dot, z dot as inputs, and x dot, y dot, z dot, x double dot, y double dot, z double dot as outputs. Or you could think of it as, on the homework, it's going to look like position and velocity, and then coming out is velocity and acceleration, where acceleration comes from the two body equations of motion. So I'm getting ahead of myself. That's on the homework assignment. For now, we're just going to talk about the pendulum problem. Okay, so how would we actually solve this? Well, first of all, let's define, and I'm going to do kind of a sloppy Python pseudocode here because I'm a MATLAB native and I'm trying to learn and become familiar with Python. We're going to define this function here, and it's going to look like this. Define some function which takes in state and time. Okay. And we're going to hard code in that gravity is 9.81. And we're also going to say that the length of the pendulum is 1 meter. Doesn't really matter. You can pick these numbers for yourself. We're then going to unpack this state. State is going to be an array, like a NumPy array, or a vector in MATLAB, where theta is the first element in state, which Python is 0 indexed. And then theta dot is the second element. Those of you that are Python natives are probably going to roll your eyes at me at some point here. I'm going to say something silly. Now, the equation of motion is that theta, I'm going to call it d dot or double dot, is negative g over L times numpy dot sine theta. And we're almost done. I'm going to say state dot is an array that includes theta dot and theta double dot, and then that's going to be our output. So this is np dot array theta dot and theta double dot. And then we're going to return state dot. Cool. So what we've done is we've coded up pseudocode of this guy, a function that takes in theta and theta dot and spits out theta dot and theta double dot. And you can kind of see the way I've coded this up, theta dot is a pass through, right? You just pass that one straight through. Theta double dot is the one that takes the math. Similarly, velocity is going to be a pass through on your homework, and acceleration is the one that takes the math. But we have the math. That's the two-body equations of motion. Okay. We didn't actually answer any question yet. All we're doing is building tools to answer a question. The question might be something like, plot the angle of this pendulum over time given some initial condition. So we'll say plot theta over 10 seconds if theta initial is 45 degrees and theta dot initial is 0. So it's starting from rest. Okay, that is a question that involves propagating a state over time. So we don't just need theta now, we need theta in a split second, and then in several split seconds. We need it again in 1 second, and then in 2 seconds, all the way up to 10 seconds. So what we really want to do is let this equation of motion go, like wind it up like you're winding up a clock or winding up like a little car, and then just let it go. So the way that we would do this is we would, going back to Python, Pythonese here, I'm going to define some time span, t span, which is going to be numpy.linspace, so a linear space, 0, 10, and num equals 100. So this is going to generate 100 numbers between 0 and 10 evenly spaced. That's what this accomplishes. And then I'm going to say state 0 for initial conditions is numpy array 45 times, we're going to work in radians, times numpy.pi 0. Oh, whoops. Who caught my mistake? I forgot to divide by 180. There we go. Now, here's the magic. State, which is going to return an array of thetas and theta dots, essentially, is scipy dot integrate dot ODEInt, or if you're a MATLAB user, this would be ODE45, and you're going to pass it a couple of arguments. First, the function, right, the func that we defined over here, the initial condition, and the time span. And we're going to let ODEInt do the heavy lifting. When you're done, state is going to be a whole, it's going to be a two-dimensional array, right? There's going to be as many values of theta and theta dot as there are values of time that you gave it initially. So it's going to go through and say, for every time that the user gave me, I'm going to find the state. So state's going to be a whole array. Theta, just the angle, is state : 0. So it's the first column of that that 2D array, if that makes sense. And this is where you would use something like matplotlib, plt.plot timespan, tspan. You know what? My handwriting's falling apart here. Let's do a little bit better. plt.plot tspan theta. Boom. So there's a very kind of quick and dirty explanation of how you would use something like ODE int or ODE 45. I will say that both of these have very good documentation, so you can go read about how to use them way better than I can describe. But this is how to use ODE int for something like a 1 degree of freedom problem, or I guess technically there's 2 states. It'd be 2 degrees of freedom. We've got theta and theta dot. I'd like you to code this up in 6 degrees of freedom using the equations of motion that we learned. So I'd like to transition to a discussion of homework 1, but I think this is a natural stopping point for the recording because the rest of this is kind of specific to our class. So any questions before we stop the recording, or are we feeling good about today's content? All right, cool stuff. So recording's going to wrap up, but I'm not going anywhere, and we're going to talk about homework 1.